Maximilians University in Munich, her MSc from Radboud University in the Netherlands, and her PhD from the European Southern Observatory, also in Munich. She then moved to Christchurch, New Zealand, where she was a Marsden Fellow of the Royal Society of New Zealand, and then to the University of California, Berkeley, where she was a NASA Hubble Fellow, until securing a faculty position at Durham University in 2020. Anna and a group in Durham used the world's largest telescopes to study star formation and feedback from massive stars in the Milky Way and beyond, comparing those observations with computer simulations. Anna is also a promoter and supporter of diversity and organizes a yearly outreach event for schoolgirls from underprivileged backgrounds in the Northeast who have an interest in STEM subjects. And I think I'm right, you're going to say something about that at the end of the talk. But the main part of the talk today is going to be about massive stars and where to find them. So over to you, Anna.
Thank you. Well, thank you so much for inviting me in the first place. I feel like I'm in a very important place when it comes to, astronomy. So I'm very honored to be here. And thank you for coming in person. And thank you, of course, also for joining online. Let's not forget that since the ominous year of 2020, this is the new norm now. That we have hybrid talks. Anyway, yes, so I thought I would talk to you about massive stars today. Massive stars are very much central to the research I do. So instead of boring you with details about my own research, I thought maybe we should just talk about massive stars themselves. And before I start, I wanted to say, if there is anything that I say that is unclear, if I say complicated things, or if I'm rushing, just stop me and ask, okay? Don't wait until the end. If you have any questions, by all means, let's make this a discussion if we want to. All right, and then the other thing I wanted to say is that you'll see lots of pretty pictures in the background. Most of these are not just there because they look pretty, but these are data sets that have been taken for my own observing programs. For example, in the background here, what you're seeing is a stellar nursery. It's a star-forming region in not our own Milky Way galaxy. This is a star-forming region in our nearest neighbor galaxy, the Large Magellanic Cloud, which you might have seen if you've traveled to the Southern Hemisphere and looked up. All right, let's see if I can get this right now. I click here, yes. So in the next 45 minutes or so, maybe 50, if you allow me some time, there are a couple of points that I would like to touch upon. So first of all, I think we need to discuss how stars form and where they form. And this is not just pertaining to massive stars, but just star formation, a brush up on star formation a bit in general. And hopefully I'll then try and convey to you that massive stars are a bit of a problem when it comes to star formation. We actually don't know yet exactly how massive stars form. We know that they're there, but the formation of them is still an open question. But obviously, once we have established that massive stars form, we want to understand why it's interesting to look at them in the first place. So sort of motivating a little bit my research. And as Peter already said, I will also talk about diversity in physics and astronomy. I was looking at the 12 pictures that are at the back of this room, and only 3 of them are women. And there is not a huge diversity when it comes to ethnical background. So hopefully we can, just reflect upon the fact that we're still needing to improve when it comes to diversity in our field. And that will bring me to one single slide about my journey to actually standing here today, I suppose. Okay, all right. So how and where do stars form? And here in the background, what you're seeing is very zoomed in bit of a star cluster that you might have heard of. It's called Trempler 14, and it's in the Carina star-forming region. So this is a galactic, capital G, so our own galaxy, star-forming region, and it's one of the most massive star-forming regions in the Milky Way. And again, this is data that has been taken with the Very Large Telescope for one of my actually early observing programs. You see the star cluster as those really bright stars over there. There's a little bit of nebulosity, which you see as fuzzy background. But really what we're interested in understanding is how the very massive stars in these type of star clusters form. So first of all, stars form in galaxies, such as this one, for example. This is NGC 300. It's not an artist's impression. It's not the Milky Way. It's a different galaxy at a distance of about 2 megaparsec. And I'm terrible at converting parsecs to light years, so apologies, but it's quite far away. And this is an image that shows you the beautiful spiral structure of this galaxy. And wherever you see white little dots, those are stars in that galaxy. And where you see the pink fluffy bits, those are the regions, the gas clouds that are being illuminated by the massive stars that have formed in them. Okay, we're gonna go into this. But just so you know, I've put that pie chart up there in the corner, which just as a takeaway message should tell you that most of the stuff that makes up galaxies is actually not stars and gas, it's dark matter. So what we're going to talk about today is the very thin slivers of that cake. All right, so stars form in galaxies, such as this one and the Milky Way and all sorts of other galaxies. And specifically, stars form in what we call molecular clouds. So here you see a little zoomed in version in a slightly different color scale of a portion of one of these spiral arms. And again, you see these kind of fluffy regions, and those are regions where the gas is being illuminated by the stars that have formed in them. And we refer to these gas clouds as giant molecular clouds. Here's I guess that color is not very pretty on the screen, but I guess you see it better on that screen or on that screen over there. This is now an image of our own Milky Way galaxy that was taken with the Far Infrared Space Telescope Herschel, which has been now retired. And here you can really see why we call these beasts molecular clouds, because it really looks like cloud structures. And wherever you see the blue kind of color, that's where, again, massive stars are illuminating the surrounding matter. And this kind of bubble-shaped morphology that you see is also because of the massive stars that sit in there. And we're going to touch upon this a while later. So molecular clouds. What kind of stuff is that? Well, it's basically gas and dust. It's gas in the form of molecules. So here I've listed just a couple, but it's mostly molecular hydrogen and some carbon monoxide. There's of course also water ices and all sorts of other molecules. I think new molecules are being discovered in space on a daily basis, basically. But these are the most common ones. So it's gas and dust grains, and most of the gas is actually frozen on top of the dust grains as a sort of like an ice mantle. And if you put all of that together, that's what we call a molecular cloud. And stars form specifically in the regions of these molecular clouds where the gas is the densest. So we really need really cold and really dense pockets of gas within molecular clouds to trigger gravitational collapse and form a star, okay? So let's just real quick go over how solar mass stars form, okay? So remember, we're gonna talk about massive stars, and when I say massive stars, I mean stars that have 8 or more solar masses, so that they're 8 or more times more massive than our own sun. But it turns out that the vast majority of stars in the universe are very much like our sun. Okay, so we refer to everything in solar masses. That's kind of our baseline unit. So solar mass stars form, as I already mentioned, in these really dense and cold cores of molecular clouds. You kind of, yeah, I guess you have to look at the side screens again because the color is a bit dark on here. But in these cold, dense regions, if you push together like a snowball almost, if you push together material enough, at some point, gravitational collapse will start. And just like you're putting more snow onto your snowball, matter is falling onto that dense region, and at some point it will be so dense that it starts to heat up, basically. It has to lose some energy and it'll start producing some heat. And at some point, you'll form a star at the center of that. And in the case of low mass stars, it's very well established that we see accretion disks that help the growth of the star around the star. So this is almost like the rings of Saturn, if you want, right? So it's like a disk of material around the equator of the star, which helps the star gather more material. And as a consequence of that accretion scenario, we also have, because of conservation of angular momentum and energy, associated jets that shoot out from the poles of the star. Okay, and this disk is actually quite important around low mass stars because at some point it will be a protoplanetary disk, and that should already ring bells. That's exactly where planetary systems will form, very much like the solar system, of course. And eventually, if you let it evolve, the planets will start clearing their orbits of the remaining protoplanetary disk material, and you'll have a finished planetary system with a central sun at the center of that. And we observe the various different bits and pieces of this evolution of the formation of a massive star. What I'm showing you here is it's a dense, very dense molecular cloud. You can't see it on the very right there. Sorry, I guess on your left. It's a dark patch in the sky, and it's dark patch in the sky because it's so dense that this particular telescope cannot see through it, okay? And that's exactly where the stars form. But if you look at this patch of the sky at longer wavelengths, you'll actually notice that there's structure in that dark cloud. And that's exactly where those high density cold gas pockets sit, where the stars will form. We also see these disks and jets from low mass stars. These are really spectacular images captured by the Hubble Space Telescope. For example, just look at the beautiful bottom one there. This is a very long jet from a low mass star that has almost finished forming. And of course, we've probably all seen these beautiful images from the Atacama Large Millimeter Array. This is HL Tau. It's a protoplanetary disk system around a low mass star. So we have observational evidence for how low mass stars form. We know that that cartoon picture in the background there is what's happening, okay? But what about massive stars now? So again, massive stars, the ones that are 8 times or more massive than the sun. And those are a problem. So let's see why. There are 2 questions that we need to answer. Okay, so first of all is why do massive stars form in the first place? And the key problem here is what we refer to as the gas reservoir problem. So to form a massive star, in some way, you'll have to funnel enough gas to a certain region to form a massive star, right? And then how do massive stars form? And that pertains to the radiation pressure problem. How does gravity overcome radiation? And this might not be clear now, but it will be hopefully in a couple of slides from now. Okay, so let's just talk about the gas reservoir problem first. Okay, so the question then is, since we now know how low mass stars form, do massive stars form exactly the same way? So is it just a scaled up version of that cartoon scenario that I was talking to you about in a couple of slides ago? Is that possible? Well, unfortunately, not really. And that's because the efficiency with which molecular clouds form stars is very low. I mean, honestly, molecular clouds are terrible at forming stars. So if you have a molecular cloud of, say, 10,000 solar masses. So you have the potential of forming 10,000 solar masses worth of stars there. It actually turns out that only 2 to 10% of all of that material will be turned into stars, right? And so now you will wonder, well, I mean, from 10,000 solar masses, I can still form a 200 solar mass star. Well, actually not really. And we're going to touch upon this a little while later, because it turns out that massive stars are also incredibly rare. So out of all of those 200 to 1,000 solar masses worth of formed stars, only 1 or 2 or a handful will be massive stars, and all the others are going to be low mass stars. And this is what we refer to as the initial mass function. You heard it, just forget that term again. Okay, the important thing to keep in mind is that the efficiency with which molecular clouds form stars is not very promising. And so we want to understand how massive stars can form anyway. So how can we make this efficiency more efficient? So people have, of course, proposed solutions to this problem. One of them is called core accretion. And I know that these are, they sound like gory details, but you'll understand in a bit why it's important to go over these things. So core accretion is what has been proposed as a solution to this. And this is just the simple scaled up version to low mass star formation. So in some way, I have this giant core of cold, dense gas, and it just collapses and forms a single high mass star. But for this to be true, we need to have these cold, dense cores to start out with. And I can tell you already, we don't observe them. There is no such thing as a massive core. All of these will form low mass stars. So it was a good idea, but these authors turned out to be incorrect. Another solution to the gas reservoir problem is what we refer to as competitive accretion. So here is what happens. You have a molecular cloud with all of its tiny, cold, dense patches, the cores, which will form lower mass stars. And these lower mass stars will be slightly closer together in the center of it, where the potential well is deeper. And because there the potential well is deeper, we can, gas falls into it, the things start to merge. And because of that merging and more gas falling into it, you're then able to grow the stars, basically, okay? So it's called competitive accretion because basically the stars in the center will suck up material from the outskirts and accrete it for themselves. And you'll end up with star clusters that look a bit like this, where you have lots of massive stars in their centers and lower mass stars sitting in the outskirts. So for this picture to be accepted as the truth, so to speak, what we need is, of course, observational signatures of this competitive accretion. Now, as I said, the hunt for these massive starless cores is still ongoing. We haven't found them, but there are good signs, observational evidence for core accretion happening. So what you're seeing here is this is an image, okay? It's an image not in the optical. This is taken with radio telescopes. But what you're seeing here, and that's indicated by those sort of purple lines here, is gas that is being funneled towards the denser patches. Those are the brighter bits at the center there. So we see this kind of conveyor belt scenario of competitive accretion happening in real time. But there is another problem, which is perhaps more important, and that's radiation pressure. So the sun shines, of course, right? It produces photons, which is why we get tanned in summer when we go to the beach. Massive stars produce many, many, many more photons than our own sun. Okay, and that can be problematic when a star wants to form, because when massive stars are still actively forming, when stuff is still falling onto that central protostar, the star already produces photons, and these photons start to push out the material that is trying to fall onto them. So what we need is to find a way around this radiation pressure that is pointing outwards, not counteracting gravity that is pointing inwards, right? Because if you equate the two, if you equate the gravitational force and the radiation force, you will come up with a limiting mass for massive stars. Theoretically speaking, stars of more than about 20 solar masses should not exist. And yet they do, of course, right? So how can we overcome radiation pressure? So here are a couple of solutions. First of all, what was proposed was, well, stars form tendentially in star clusters. So in regions with a high concentration of stars. And if the concentration of stars, if the density of stars is high enough, maybe you can have stars that merge a bit like these merging black holes to form a more massive one. But for this to actually happen, the density of stars in space needs to be so high, because otherwise you don't have encounters between stars. Believe it or not, space is incredibly empty. Okay? Even when we see something on a picture that looks like it's very packed and closely together, there's vast amounts of space in between those stars. So the density of stars needs to be so high for mergers to happen that this is actually not a realistic solution to this either. Okay. There simply aren't star clusters with these high densities. It works very well if you simulate them. Simulations can produce basically any answer you want, but then observations are the truth, and we just do not observe them. But what we do think is happening, and this is basically what the next about 10 minutes will be about, is accretion disks. So we already saw accretion disks in low mass stars. And the question is, do massive stars have these accretion disks as well? Because if they do, that would be very handy in the sense that the accretion disk kind of would shield the equatorial zone of the star from the outward pointing photons, such that material can still accrete, fall onto the star in that region. And all of those nasty photons that want to stop the star from growing are beamed towards the poles outward. Okay, that's what this radiation beaming is all about. It turns out that early simulations of this formed stars of about 40 solar masses. But as you probably all know, we observe stars that are even more massive than that. Especially in the early universe, most stars were 100, if not more, solar masses. Okay. Now, if massive stars can form via disk accretion, what we should see is the same as what we observe for low mass stars, right? We should see jets from young stellar objects, which is that nasty acronym there, just like we observe them for low mass stars. And we have now, and this has been observational evidence that has been only available to us in the last, I want to say, not even 10 years. We now have observational evidence for accretion disks and jets from massive stars. So let me give you a couple of examples. The first one, I apologize, is not very spectacular. Okay? This is an object called HH8081. It's a star of about 10 solar masses that has formed in the Milky Way. It is launching a jet that is actually quite long. It's about 32 light years long. Okay? And you can see the jet in these radio images, which are the sort of blue background ones. The central bit where most of the color is, that's where the star sits. And then that elongated sort of shape, that's where the jet is propagating into the interstellar medium. And if you look if you look at that in optical images, what you see is actually that green emission up there. So that is where the jet is interacting with the interstellar medium around the star, and it's creating these beautiful shocks. It's shocking the gas, and the gas is very high temperature. It's about 10 to the 6 Kelvin, so it's quite hot. And that's what we see in the optical and X-rays. So then there's another one. This one is in what is probably most of people's favorite star-forming region, the Orion Nebula. Okay? And this is Orion Source 1, observed again, in the radio wavelength, so with the Atacama Large Millimeter Array. This was performed by a colleague of mine, Adam Ginsberg. What you see on the left side here is, of course, an artist impression, but that sort of should give you an idea of what a young, accreting, forming massive star should look like if you were able to see it properly. So you see the accretion disk, that little bit in the center that shines, that's the star. And then you have this massive kind of outflow jet-like structure launching out from the poles of the star. The central image is what they actually observe. So it's not too dissimilar from the artist's impression. And I think, we were just talking about technological advancements before starting today. And I think it's amazing that we can observe these things nowadays. And here's another one. This one is called AFGL 4176. This is a 12 solar mass star. It has an accretion disk that is, we refer to this as Keplerian, and that's just because the motions of the gas follow Kepler's law. And that's what these funny kind of rainbow-like pictures show. We're not going to go into that. But just for reference, okay, I showed you the disk of HL Tau before, which, if you remember, is a disk around a solar mass star, or actually perhaps a star that is not even solar mass, right? Yeah, you can't properly see it on here, but it's tiny, okay, compared to the disk of AFGL 4176, right? This is the actual scale comparison. So these are beasts in the sky. Okay. Now, all of these examples that I've showed you so far of accretion disks around massive stars that are still forming are very compelling, and they're great. They helped us understand a little bit how massive stars form. However, they're all in our own galaxy. And while we all love home, our own galaxy is just simply not representative of the vast zoo of galaxies and different types of environments that are out there in the universe. And in order to understand star formation, especially massive star formation, which was so incredibly important in the very early stages of the universe, where most stars were massive, we need to look in environments that are more similar to those of the early universe. And the Milky Way simply is not that. It is not an environment that we can take as a template for the early universe. Luckily, our two nearest neighbor galaxies, the Large and the Small Magellanic Cloud, which we already encountered earlier, are more similar to the conditions of the early universe than the Milky Way. So they should be an ideal test bed to see if we can use them to study star formation in these earlier times of the universe. Now, of course, the trouble is that they're far away. It's convenient to study stuff in the Milky Way because it's close by. At the same time, studying things in the Milky Way can be tedious because there's just so much material between us and the object that we want to study, because we're sitting right in the Milky Way, right? That it's also difficult. Now, if we wanted to observe massive stars as they form with their accretion disks around, in external galaxies, we really need to make a big jump in terms of technology. And the most recent upgrade to the Atacama Large Millimeter Array has made that possible. So we were able to detect the very first accretion disk in our galaxy that is not our own, around a forming massive star. Now, this is an object called HH 1177 in the Large Magellanic Cloud. So this is, again, our nearest neighbor galaxy. It's actually a satellite of the Milky Way. The mass of the central star is about 12 solar masses. It has a beautiful jet, very similar to the one I showed you earlier around HH 8081. But most of all, it has a ginormous accretion disk, okay? It's about 6,000 astronomical units. Just to put things into perspective, an astronomical unit is the distance between us and the sun, okay? Let's see. I think Cassini might be at 60 or 100 AU by now, something like that. But for sure, all of the planets in our solar system are not beyond 10 astronomical units. And this disk is 6,000 astronomical units in radius, okay? So that's 12,000 in diameter. It's a beast. Let me quickly walk you through this. So in the background there, you can see a beautiful image taken by the Very Large Telescope. And it's a color composite, and the colors here should show you, where the gas is. And while we were inspecting this image, what we saw was this kind of wispy-shaped structure up there. We refer to these as pillars. You might have seen the famous pillars of creation in the Eagle Nebula, basically the same kind of gas structure. And at the tippy top of that pillar, a star has formed, which is the star of this particular object, that 12 solar mass star. And what you see in this gas image are these kind of bow shock shaped structures. You can see them, I guess I was pointing on the computer so that people online can see. But you can see sort of these arch structures. You can see it in blue above those two pink point sources up there. That is where the jet that is coming from that star is shooting into the interstellar medium. And as the jet shoots into the interstellar medium, it kind of like when you're sorry. As the jet shoots into the interstellar medium, a bit like when you're swimming, right? You have this bow in front of you, and that's what you're seeing here. And indeed, if you do a clever, thing with your image, you're then able to see the actual jet, and that's that lower image where you see a blue portion. So the star, the driving star, the massive star, is the pink bit, is that pink point, and from it you see the two sides of the jet. One is colored in blue and one is colored in red. And that's what astronomers love doing to indicate something that is moving away from you, and that's the red color, and something that is moving towards you, and that's the blue color. So this particular jet is oriented like this. So the upper part is pointing towards us as the observers, and that's the blue, and the red part is pointing away from us. Right. So because this was pretty cool, it was published in Nature twice. First, the discovery of the jet, and then the discovery of the accretion disk itself. And again, I mean, this is cool not because it was published in a high impact journal, but it's cool because we have never ever observed such an object outside of our own galaxy. And it really now serves as a proper benchmark for studies of star formation in conditions in environments that are not those of present day Milky Way. Okay, so we now know that disk accretion and jet launching are observed in massive forming stars. Okay, and we know that at least up to 20 solar masses, this is how massive stars form. But what about, what now? We know that massive stars exist, and we think we have at least an initial understanding of how they form. But why do we care about them at all? Is, I think, the most important question. I mean, at least that's what gets me up every morning and go to the office, okay? And the key word here is feedback, okay? Massive stars, although they're very rare and they only make up 1% of all of the stars in the universe, their energetics, so their output in terms of energy vastly dominates over all of the low mass stars. So if you have 1,000 low mass stars and one massive star, the energetics of the entire star cluster will be dominated by that one single massive star. And you can forget about the radiation from all the low mass stars. And I referred to this initially before already. This is what we call the initial mass function. And just so you can visualize it, right? So for every 200 low mass stars, we only have one massive star that forms. That's how rare they are. Okay, so feedback from massive stars is really energy that they output and momentum that they output. Or in other words, they heat their surroundings and they kind of push their surroundings aside. They move stuff, which is why we observe these beautiful bubble-shaped star-forming regions in the first place. It's because there are massive stars sitting in them that have inflated those bubbles that are illuminating the gas and making it really pretty for us to look at. Now, feedback is a bit of an umbrella term for a couple of different physical mechanisms via which massive stars interact with their surroundings. So of course, we've seen these jets and the outflows from the massive stars as they're forming, right? That propagate into the surrounding interstellar medium and create these shocks and so on. Then there's, of course, the pressure of the radiation, so the pressure of the photons pushing onto the surrounding gas. Let's not forget that the gas is being also ionized by the photons that impinge on it. And that means that basically every gas atom, or not every atom, but the gas atoms lose one or two or more electrons. That's what ionization means. The electrons are kicked out from the atoms. Then there are, of course, stellar winds. We know that, right? When we observe northern lights, that's the interaction of the solar wind with the magnetosphere of the Earth. And then, of course, supernovae, let's not forget about those. Massive stars are cool also because they die with a bang, right? Okay, and so this feedback stuff that massive stars do, yes, it's true. It originates on the small-ish scales of the individual stars, but it turns out that it has profound effects up to the scales of entire galaxies. If it wasn't for massive stars, galaxies would not look like what they do. Okay, you can simulate that. I'll show you in a second, but just to give you an idea of what this feedback does. So on that, on the left-hand side, what you see there is the Orion Nebula. Taken away the stars, we've magically removed the stars of the Orion Nebula from this image. That's a central part of the Orion Nebula. Okay, it's about 1.6 light years across. And it looks the way it does because of the massive stars that we have conveniently in this image taken out. Anyway, I already mentioned the pillars of creation, but there are many, many more beautiful examples of these kind of pillar-like structures in different star-forming regions. It just happens that this particular region was observed with the Hubble Space Telescope in 1991, and that image was so fantastic that you can find it on mugs, t-shirts, hats, blankets, pajamas, and all sorts of other stuff. This is not the Hubble Space Telescope image, by the way. This was taken for one of my observing programs with an instrument called MUSE on the Very Large Telescope in Chile. And these pillar-like structures look the way they do because they are being shaped by feedback from massive stars. Okay. Right, so this is a slightly larger scale. We're about 5.5 light years across here. Just to put things into perspective, the solar system is about 8,000 parsec from the center of the galaxy. So these are seemingly small structures. But as I already said, massive stars have a profound impact on the scales of entire galaxies. Now, what I'm showing you here is a simulation. It's actually two simulations on the two different panels. One simulation, it's a simulation of a galaxy. Okay, so it's one single galaxy that wants to form stars. One simulation, the one on the left, has been seeded with a lot of feedback. So take, or pretend like there's a button on your computer that says amount of feedback. And if you crank it all the way up, okay, what is going to happen is that the galaxy will just sit there and not do much at all. It won't form any stars, basically. And that's why there's lots of pink stuff there. That's just gas that is sitting there and not doing much, okay? But if you turn all of the feedback from massive stars off completely, then the galaxy is going to start forming stars in a crazy way, almost in a runaway scenario. And most of the gas in the galaxy will be turned into stars. But of course, we know that the reality is somewhere in between these two extreme scenarios, right? It looks something like this. Galaxies form stars, not too many, but still. So without feedback from massive stars, the universe would just simply not look like what we observe it to be. Without feedback from massive stars, your simulation is not going to produce realistic results. But then, of course, the next question will become, what is the right recipe for stellar feedback that you need to put into your simulation in order to make it look like that bottom image there? This is an observation, okay? And this is an entirely different talk, which we're not going to get into, but that's what I work on. Okay. There's, however, one thing that we have not talked about, which is a different kind of feedback. And you see the periodic table here. Are the chemists somewhere on the premise here as well? No? They're over there, okay? They'll be happy that we show this here. Don't tell them that everything after hydrogen and helium we refer to as metals, because they would not be happy with that. Anyway, so another thing that massive stars do is they produce most of the elements on the periodic table. We call that chemical enrichment. Okay, the universe started out being basically helium, hydrogen, and just a tad bit of lithium. And all the other elements here were produced inside massive stars, inside the very first massive stars. So let me put the importance of this chemical enrichment thing into perspective. I'll tell you a story now. It's not going to be long, don't worry. Okay. The story goes like so. A long, long time ago, in the very early universe, I'm reading this to you because I realize that the font is not super, okay? The dark ages are coming to an end, and the first generation of massive stars exploded as supernovae, liberating the first elements heavier than lithium. First molecular clouds are starting to form proper stars. So just to orientate you, we're here, okay? This is sort of from the Big Bang to modern times. We're here, and the story we're telling begins at the very beginning of star formation, basically when the first galaxies and stars formed, okay, after the dark ages. Now, these supernovae explosions really inject enormous amounts of energy into the interstellar medium, but also, of course, these heavy elements. Okay, so this is the Crab Nebula you can see in the background, or you cannot see in the background on the screen. But just imagine peppered heavy elements sitting in the remnant of that supernova explosion. The star was torn apart and it liberated all of those heavy elements, okay? So perhaps out of that leftover material at some point in cosmic time, it will be able to cool down and reassemble and form a new star. Maybe it's a low mass star, like the one that you're seeing in this image here at the very center, it shines. It still has the leftovers of its accretion disk around it. This is now a protoplanetary disk. And those heavy elements have made their way onto the protoplanetary disk. You can see there is a planet that is starting to form, very much like when you start pushing a snowball down a hill. That's exactly what's happening here. As that initial bit is orbiting around the star, it just gathers more and more material just because stuff sticks to it, and it will eventually perhaps become a proper planet, a planet maybe not too dissimilar to our own, okay? So really what massive stars contribute to is a ginormous cosmic recycling system. And when people philosophically and romantically say you're all made out of star stuff, that's actually true. Everything in here, everyone in here was once inside a massive star. Okay, every single atom in your bodies, in the woods, in the carpets, everything. And I think that's pretty nice. Anyway, so this concludes the first bit of my talk, and the last bit is going to be much quicker, no worries. I'm almost done, but just let's summarize the sciencey bit. Massive stars are cool. I hope that this is not only valid for me, but as of today, you also think that massive stars are cool. We have now begun to understand how they form and where they form. But of course, there are still lots of open questions. Like, for example, what are the initial conditions of the very first massive stars? How do stars with crazy amounts of masses form, like the ones that we found in the early universe? And how exactly does this feedback stuff work? And how can we help our friends who do the simulations to make better simulations? Okay, so next steps here would be to, of course, observe more of these disks around massive stars, around more massive stars. And I'm not going to go into this, but there are problems associated with that. We want to do more studies in terms of feedback, and that's what my research group is doing. We want to make simulations much closer to reality, based on the empirical inputs that observers provide to the simulations. We want to build many more telescopes that are, even better than the ones we have now, with higher angular resolution, higher sensitivity, and bigger mirrors, and you name it. We want that. We need that, okay? And so on and so on. But I would like to spend, if I have a little bit of time, okay, I would like to spend a couple of slides on what Peter already mentioned is very important to me, and that is diversity in physics and astronomy. And what you see in the background here is what I was trying to refer to earlier, right? The Milky Way simply is not representative of the vast zoo of galaxies that are out there. And I think the same is true when it comes to people, right? I'm not representative of the human species, neither is any one of you. And it's nice that we're all different. So before I motivate this, let me just give you numbers, okay? First numbers and hard facts, and then we try and unpack that. Unfortunately, there is not a whole lot of numbers available yet. So what I'm going to show you here is data coming from the United States. And specifically, these are percentages, okay, of physics PhD degrees earned up to, I think, 2017, split up by gender. Needless to say, the top ones are the male, and the ladies are hovering around, the 20%, call it, mark. So this, is fluctuating, of course. And this plot goes back to 2011. But if you were able to go back even further, you would see that curve has actually grown quite a bit. And now it's plateaued at 20%. We really have a hard time getting it higher than that. This could be yet another talk entirely. I just wanted to show it to you. We're not going to go into ethnicity at all, but it's just to demonstrate how bleak the situation is when it comes to ethnical diversity, okay? Gender diversity, ethnical diversity. Most of us have a white background, and we need to make that different, okay? Closer to home, perhaps. What I'm showing you now is, never mind the color bar, the numbers at the top, but this is basically the percentage of an entire GCSE cohort who choose to do physics GCSEs across the country. And what you see is that in the South, there are many more students taking GCSE physics than in the North. If you split that up by gender, you immediately see, the middle is boys, and the right-hand side is girls, you immediately see that not only is the Northeast doing worse when it comes to pushing students into GCSE physics, but there aren't really many girls at all who take physics GCSEs, okay? So fewer kids take physics GCSEs in the Northeast, and this is particularly true for girls. In fact, if you have a look at the percentage of enrolled undergraduates by gender in a variety of different fields, so we have physics, physical sciences, and then all subjects is the yellow bar here. Again, you see that girls really only make up that sort of 20-ish%. Again, this is at university now, and at Durham University, we are not doing much better, okay? So this is just to say that the number that you should keep in mind is that women in physics and astronomy is slightly better than physics, but the number you should keep in mind is about 22%. That's sort of the amount of women in the field. So physics and astronomy are simply not yet diverse fields, right? But why should we care at all, besides the fact that it's morally right to do so, okay? And this is a beautiful cartoon, I think, that should really illustrate and drive the message home. So here you have an assembly of different types of animals, right? And a clever guy sitting there and saying, for a fair selection, everybody has to take the same exam. Please climb that tree. And immediately you'll see that the fish will have a bit of a hard time, right? But at the same time, what you want to do is you want to give everyone a chance, because your team might need a fish eventually, and your team might need an elephant eventually, even though they were not able to climb that tree in the first place, okay? There is also evidence to back this up, okay? This is evidence gathered by the Institute of Physics. So just as an example, okay, at McKinsey, they made a study and they found that firms that have a gender diverse plan and gender diverse leadership outperform the others by 25%. That is a huge number, okay? And ethnically diverse firms did better by 36%. So even if you don't care about the moral situation, hard facts don't lie, okay? If you are a leader in any kind of position, you want to have a diverse workplace. So one of the things that we're trying to do in terms of getting at least more girls to get into STEM subjects, if not physics and astronomy, is this initiative at Durham University, where for one day we invite girls from really underprivileged schools in and around County Durham to come and spend the day with us. They get all sorts of fun stuff and fun activities to do. And we now have evidence that this is actually really working. We have had now 2 students who came to one of these events who have enrolled in physics at Durham University directly. So it is working. And there's plenty of other outreach things that we do to help this. And I also want to mention, it's good to do this at high school level, but really the problem already starts at elementary school. So that's where you have to start to capture the kids' minds, because that's where the difference between boys and girls gets put into their brains. Girls are told, you're not going to be good at maths. Boys are good at science. Here is a set of Lego for you to build, little boy, and here is a Barbie doll for you, little girl, okay? And just one last thing about this is that we also do a lot of work together with teachers, because it turns out that many teachers are unconsciously biased. They themselves perpetuate this problem. They will give higher marks in STEM fields to boys than girls, okay? They don't do this on purpose, okay? It's an unconscious bias. But once you tell them that, it's a first step, okay? And everyone, even you here in this room, you can do your part. If you have kids, nieces, grandchildren, friends, or you name it, you can do your part, right? First of all, you can actively seek out different points of view, right? You can start using gender neutral language in your daily life. You can stop buying pink clothes for your daughters. Pink is a great color. I love it. Don't get me wrong. But again, we want to get away from that perpetuating and all sorts of stuff. I can put the slide up again if you want to later. And I'm getting onto my very last slide and then I'm going to be done. Okay. Because even if you manage to get a girl to study physics and have her finish and have her get her PhD degree in a related subject, retaining women in STEM fields is incredibly difficult because of what we refer to as the leaky pipeline, okay? As a function of seniority in our fields, you have women drop out because they have kids, they decide to, leave their job to raise a family, because they feel it's a toxic environment, because we are only 20% of everybody else. And so we really need to do a better job at also retaining girls once they are in the field. And that's why I will show you the slide just to, kind of illustrate that the leaky pipeline, even though it sounds bad, it can be fixed in some way. And so the title is sometimes The Road to Your Dream Job is not a straight line. But I could have called it the leaky pipeline sometimes, can be patched. So when I was in high school, I was awful at physics. Like I was not very good at all, to be quite frank. I partially blame it on my physics teacher, but who knows? Anyway, I liked physics quite a bit, but I just simply didn't think it was for me. So what I did instead was I pursued a degree in nursing, and that's because when I was in high school, I was volunteering for the local ambulance service. And these were the times of that TV show that made George Clooney famous, ER, if you remember. I thought that was cool, so that's what I did, right? I became a nurse. But I really did like the stars, and this is me looking through a telescope back when I was still doing that kind of activity. Yes, this is during the day, but we were just calibrating stuff. And I realized by looking at Jupiter there with 4 of its moons, this is a picture I took through a tiny telescope, I realized that I have no idea how any of this works. Like I really don't, and I really, really need to know. So I decided to go back to university, or go to university, and get a degree, and that's what I did. I did my bachelor's, master's, and then I got my PhD. But unfortunately, here the leaky pipeline kind of hit. Because my husband got a job at a university where they did not have a job for me, I had to leave academia for a while, and I worked as a software engineer. It was the most awfully boring job I have ever done in my life. In fact, I resigned 6 months later because I thought, nope, this is not what I want to do. Fortunately, in the meantime, I had applied for a research grant. It was the only research grant available in the country we were in, which was New Zealand. And I ended up getting that grant by the Royal Society of New Zealand. So I managed to go back to academia. But just to realize, right, this is really, it was a lucky happenstance. Most people are not offered that opportunity. And so that really kickstarted my career. I ended up, being a fancy NASA Hubble Fellow at one of the most prestigious universities in the States, at Berkeley. And then I joined Durham University as a member of the faculty 4 years ago now, and that's where I'm at. And yes, that's actually everything from me. So thank you for your time, and I'm sorry that I went over a bit. Thank you.
Does that work? Is it working? No, that's better. Thank you, Anna. And that's an important point to end on. And thank you for reminding us of the importance of diversity action. And it's something, I will point out, is something that's very important to the Royal Astronomical Society as well. And indeed, as Anna indicated, you as friends, you're members of the Royal Astronomical Society. And so anything you can do in that direction would be helpful. And please utilize the resources that the RAS has available to help in that direction. So if you want to get involved in something or volunteer for something locally, then I'm sure the RAS would be very happy to help you. And so, you can talk to me about that if you want to. Questions about massive stars, though, please.
I'll talk now, Nick.
Yeah, the trouble is people
I can repeat the question for the people online.
Yes.
Yeah.
You mentioned turbulence awareness. I wonder if the turbulence from the first massive stars disrupts the ecology of the molecular cloud so much that only small stars can form up. Because once you've got some angular momentum swirling around, it's going to be much harder to form massive stars in the future.
Yes. So the question is about turbulence from the very first massive stars and whether that turbulence might not have, or why does it not lead to basically only massive star formation, right? Yeah. So the answer again is chemical enrichment. The chemical content of a gas is actually incredibly important because all of the cooling of a molecular cloud happens because of the presence of metals. And so the more metallicity you have, the more heavy metals, the more efficient cooling will be. And so because of these massive stars enriching their environment over and over again, you also allow for more cooling. And we know now, right, that you need cool, dense things to form stars. Sorry, I'll have to come closer. Plasma, okay? Okay, so this is, I guess, a very technical question. If I understood you correctly about plasma inside the stellar interior. Or like the gas structures. Yeah, okay, yes. All right, so the question is about internal plasma motions to stars and how, the bigger events might lead to differences in terms of evolution of a single star. Okay, yes. Yeah, so that is an entire research field on its own, and it's not my research field. It's stellar structure and evolution, but I will try and give you a sort of big picture answer to this. Right. So yes, the physical mechanisms like plasma motions inside a star and convection and all sorts of stuff that goes on in the different layers within a star are incredibly important because they will set the evolutionary pathway a star might or might not take. And that also includes how fast a star rotates. That will also dictate how stuff moves within it, right? And how hot the star is. So all of these factors combined will for example, set how strong the stellar wind is, so how much mass the star loses. And that's really important because massive stars lose an incredible amount of mass during their lifetime, and the amount of mass the star loses will then determine whether it can go supernova or not, for example. Yeah. Yeah, so Exactly. Yeah. Yeah. So there are people who simulate how, you know, the structure internal to a star affects the evolution.
Sorry to interrupt. Maybe we could take that offline as a discussion. I'm conscious that other people might.
Yes. I don't know if there are
any questions online. So nothing. Any more questions in the room? I just want to have this one, please.
Just when you talk about the massive stars in the early universe, the population of the stars, I just saw you there.
Sorry, what was the last part? Well, so here's the thing, right? The very early universe is not only very early, but it's also very, very, very far away. So observing single stars is basically impossible even in the nearby universe, okay? So we can observe single stars up to a certain distance in the nearest nearby galaxies, but even beyond that, it is really hard to observe individual stars. We know, though, that they are there because of the effect they have on their environment. So, for example, how much a gas is lit up depends on what kind of stars sit in that gas. And so we can kind of infer the mass of the stellar population in a very, very distant galaxy in the very early universe, just by not seeing them, but by seeing what they do to their surrounding gas. So it's inferring rather than direct observation. Yeah, so the question is if the Square Kilometre Array, the SKA, which is a next generation radio telescope that is being built in Australia and South Africa, if that will help us. The answer is yes, because this radio telescope will have what we refer to as really long baselines. The longer the baseline of a telescope, of a radio telescope is, the smaller the structures in the sky are that you are able to observe. So yes, we will be able to peer further than ever before. Yeah, it will help.
Okay, unless anyone's got a burning question, time's kind of.
Yes, sorry.
Probably thank Anna again for a massively interesting talk. Sorry.
Unintended.